All right, so today we have Daniel Brennan, who will tell us about the Callan Rubakov effect. Take it away.
All right, great. Thanks, Julius. And yeah, thank you very much for the invitation. It's really cool to be here at the Quiver Meeting. I've heard about this for a long time, but I've never actually had the chance to attend because of time zones. But nevertheless, I'm very glad to be here. Yeah, so today I'm going to tell you guys about, excuse me, something called the Callan Rubakov effect. And so this is a really old problem in monopole-fermion scattering. So the idea is you start with some UV theory, which is some sort of G gauge theory for G non-abelian, and you add some adjoint scalar, and then you consider an RG flow where you go to the infrared where you condense the scalar field. So when you do this, the infrared can generically become some sort of U1 abelian gauge theory. And along this RG flow, the smooth monopoles flow to the Dirac monopole, or also known as the monopole line operator. They're also sometimes called the 't Hooft operator. Is there an incredible delay?
Possibly. Right now, Dirac monopole operator is written.
Okay.
It's done now, though.
Okay, I'll try to. Okay, I'll try to time it then. All right, very good.
Okay.
So if you also add charged matter to this UV theory, so some sort of charged fermions, and we want to do this without Yukawa coupling, then in the infrared, this leads to charged fermions. That are generically massless. Unless you add some mass in the UV and then they flow to some massive fermions in the infrared. And so the Callan Rubakov effect is about the interaction between these Dirac monopole lines and those charged fermions in the infrared. So traditionally, the Callan Rubakov effect is phrased in terms of a gut theory. So Callan Rubakov is for guts. So we're in this setting that I phrased it, but you can also ask the question totally in terms of this infrared effective field theory, where you have any sort of U1 abelian gauge theory with some charged fermions, and you can ask what happens when they scatter off of this Dirac monopole line operator. And so the original reason why people were interested was this gut setting. And what happens is that if you imagine our sort of Dirac monopole as some very heavy ball where there's a magnetic field coming out of it, and imagine some classical particle, some sort of charged fermion that's coming in. So if it comes in exactly along a magnetic field line, there's going to be zero Lorentz force. And what that means is it's literally just going to run straight into the monopole and bounce off of it with some sort of hard sphere scattering. So in the quantum theory, what this means is that charged matter can interact with the UV degrees of freedom inside of the monopole core. And so this was originally studied, as I said, in gut theories. So this is in the context of particle physics. this is important because gut theories traditionally break the symmetry of the standard model, which is known as U1 baryon number. And because of that, this is thought to shown to rather lead to proton decay. And what's particularly interesting is that because there's this, essentially just because there's a magnetic field coming out of the monopole, so usually there's this sort of scattering cross section, which is scales like 1 over the size of the monopole, so it should be suppressed by the UV scale. But the surprising part about the Callan Rubakov effect is that I found it was actually an order 1 scattering effect. So this is supposed to lead to some very large and observable proton decay. So this is also sometimes called proton catalysis or proton decay. Cool. So this is sort of the historical version, but this what's very cool about this, from a more formal standpoint, is that it's a very explicit example of a theory with UV IR mixing. And this is sort of just a generic feature of bulk defect interactions. And this is just one example where the dynamics have been studied for a very long time. And so we know a lot about it and sort of a lot of the things that are confusing about it. So indeed, the thing that is considered the most confusing about the Callan Rubakov effect is that if you do the analysis, especially using symmetries, what you find is that if you take a proton and you scatter it off of the monopole, what you find is that you get some proton catalysis, so it turns into some positron for gauge. Essentially what it does is it turns into a proton, you get a monopole, and then you get a bunch of other junk out. That's sort of constrained by the it's constrained by the non-anomalous, and by anomalous I mean ABJ anomalous symmetries of the problem. So in the case of the standard model, we're taking everything to be massless. So in the infrared, there's actually a lot of there's a lot of accidental symmetries in the theory. And so what's confusing is that not that it takes this form, but rather this, if you just look at the analysis, looks like some sort of fractional fermion state. Or rather some sort of direct sum of fractional fermion states. And I'm going to explain what that means later, but by actually just showing you the analysis. But essentially, there's been so much confusion about what these are over the past, I guess, about 40 years now. And so there are some important comments to make about why we even think that this analysis that we're going to do makes any sense. So the first is that everything we've done here is totally in the semi-classical regime. If we pick our UV theory to have a sufficiently weakly coupled weak coupling, we take our the VEV of the Higgs to be sufficiently above the confinement scale. Everything is totally weakly coupled. We have total control over everything. Everything is a smooth field configuration. This is just literally a problem in field theory. So that's one comment. And yeah, so that's sorry, I guess that's the main comment. But so sort of using this analysis, there have been roughly 3 major attempts to explain the problem. So proposals. Actually, is there a? Okay, I'm too slow to do this in real time. Okay, right. So the first proposal was given by Callan, actually, is that the fractional fermion states can be understood in some sort of density matrix, which is of course a very natural thing to guess. But this has a very critical issue, is that essentially what it says is that gauge invariance is only conserved up to classical probability. And that's bad. Good. So another sort of classic proposal, which actually has very many iterations, is that actually there exists extra non-perturbative sectors of the Hilbert space that are only activated in the presence of a monopole. And so this is actually this is a very tempting proposal because it sort of works with every symmetry. Sort of everything is really nice, except that this essentially is saying that our assumption of the semi-classical regime is bad. And it's not just that, or sorry, the semi-classical approximation is bad. And it's not just that the semi-classical approximation is bad, is that the asymptotic Hilbert space is totally different than you expected from sort of a free field quantization. And this sort of goes against many of our sort of intuitions about quantum field theory, such as clustering. And so the third sort of class of proposals is that maybe there are additional interactions that we missed in the analysis. And there are some sort of ideas that these interactions should be possible. So for example, if you're working in a spherically symmetric approximation, which is what we do usually, and we're going to do, it solely talks about the total angular momentum being 0 or fixed rather. And so that doesn't actually constrain the individual particle momenta. And so there could be these sort of additional sectors where you sort of have these entangled states that could contribute to the process that we've missed. But there's sort of, as of yet, there's sort of been no proposals for what this interaction is or could be. So today, we're going to propose a sort of, actually a sort of new interaction that could explain the Callan Rubakov effect. And so first what I want to do is I want to actually show you the sort of original analysis and sort of show you what goes wrong, and then sort of show you sort of what we missed and how this could potentially solve the issue of the question of the Callan Rubakov effect. So I don't know how many people are actually currently attending, but I welcome questions at any time from anybody. Usually makes the talk a little bit more fun. Okay. All right, cool. So, all right, so let's just go ahead. So let's review the sort of old analysis of the Callan Rubakov effect. I guess I'm gonna let my writing catch up. So here the setting is some 4-dimensional SU2 gauge theory. And we're going to couple it to one adjoint scalar. Just adjoint scalar. And we're going to couple it to 2 times NF fermions in the fundamental representation. So picking an even number so that there's no gauge anomaly. So now this theory is totally well defined. Everything's nice. And we're going to say this theory only has gauge interactions plus a potential for the scalar field. We can just pick this to be the standard Mexican hat potential, for example. So this theory in the UV flows to a U1 gauge theory because this potential causes the scalar to condense. Because I can write it exactly. And the UV cutoff scale of this theory is going to be given by the mass of the W boson, which is the gauge length of the UV theory times the Higgs Bev. And as I said before, the smooth monopoles of the UV-SU2 gauge theory become the monopole lines in infrared. And because there's no Yukawa interaction, the fermions remain massless. along the flow. So, oh, sorry. So I apologize for being a little bit discombobulated. I usually give this as a board talk. I do want to say that I need to say, actually, there's something important that I'm going to do that people usually don't do, which is actually very helpful in understanding what's going wrong. So one of the major things that I did differently than what people did in the past is that I really focused on the case of massive fermions. And there's sort of two reasons why I took this approach. So the first is maybe a bit silly for a formal crowd, but the reason is essentially for phenomenology. In the universe, we think that there's no massless fermions. And so if you want to understand what's going on in the real universe, you might want to consider massive fermions. Of course, all the fermions in the universe have different masses, and I like symmetry, so I took them all to be the same mass, but anyways, it's one step in the right direction. But probably the more important reason I wanted to consider massive fermions is that the fermion mass actually acts like an IR regulator. And that's really important for a couple of reasons. So if you have QED with massless fermions, actually there's a lot of very strange things that happen. So for example, if you have a central potential, then charged fermions don't form a bound state. There's nothing wrong with this, it's just very strange. And also, I believe that massless QED actually has a lot of issues in terms of properly defining IR, or the sort of asymptotic scattering states. I believe the sort of Faddeev-Coolidge states actually might be not well defined. Anyways, this gives you a nice IR regulator and makes, as we'll see, it sort of makes some of the problems go away. All right, sorry. Good. So for now, what I want to do is consider the massless case, which is what people originally studied, and then we'll go to the massive case and show you sort of how things are much nicer in that setting. Okay, good. So, right, so we're looking at this RG flow, and I want to focus on a class of monopoles. So first, let's study the bosonic sector, and then we'll couple the fermions. So we're really just focusing on the gauge field and the Higgs field, and these are sort of what comprise the smooth monopoles. And there's an infinite number of monopoles in this gauge theory, but I want to focus on a particular type. So I want to look at ones that are spherically symmetric. And BPS.
Could I ask a few basic questions?
Yes, please.
So there's a strong coupling scale for the SU2, there's the VEV scale V, and there's the mass scale for the fermions. Are you taking what order are you taking, or how are these related?
Yeah. Good. So I'm taking the VEV scale to be much higher than much higher than the confinement scale. So I guess we sometimes call it lambda QCD. And I'm also taking, just by saying that we have some weakly coupled theory, I'm taking G to be very small. And I believe I want to take the scale where B is much bigger than mass of the W boson, which is much bigger than lambda QCD. So here everything is totally semi-classical and very well controlled.
Great, thanks.
Okay, cool. Oh, there are many people here. Okay, very good. Okay, great. Yeah, so I'm taking the spherically symmetric limit, and I'm going to take the BPS limit as well. So the spherically symmetric limit is just so that we can sort of use spherical symmetry to make the problem significantly easier. And so for a spherically symmetric monopole, we mean is one that is invariant up to gauge transformations. So what we can do is we can sort of supplement or enhance the sort of standard orbital angular momentum generators by some gauge transformation. So we pick some SU2 embedded in some sort of SU2 rotation that's embedded inside of the gauge group. And we demand that the monopole be invariant under these modified generators. And as it turns out, there's sort of, Okay, one more comment. So I also want to take the BPS limit, which is the case where we sort of ignore the effects of the monopole of the scalar potential. And this is also sort of for convenience, just because we actually have exact solutions for BPS monopoles, but not for non-BPS monopoles. And the only sort of physical effect of turning on this potential or taking into account the potential is that it should just sort of squeeze the core of the monopole, but it really shouldn't change any of the physical effects. Good. So in the SU2 gauge theory, it turns out there's actually a unique, spherically symmetric BPS monopole, which is great. And it's just the minimally charged BPS monopole that we know from supersymmetric gauge theory. So I can write the connection explicitly, as I was saying. So you take the Dirac monopole. So I'm going to work in a singular gauge. So you take the Dirac monopole embedded along some diagonal direction in the SU2, and then you have some exponentially decaying off-diagonal components. Minus I cos, oh, okay, right. So it takes this form once it finally loads, and the Higgs field also takes some non-trivial profile, which is also along the diagonal direction in this gauge. So the picture is that, so they're saying there's this function m, which falls off exponentially with the W boson mass, and the Higgs profile goes to a constant plus some 1/r fall off up to exponentially good order, up to exponential corrections. So the picture, once the thing catches up, is the following. So the Higgs field has this sort of core. So it starts off in sort of 0, and then it goes up to a constant approximately. And this core size here goes like 1 over the W boson mass. And the off-diagonal component of the gauge field, which I'm going to just colloquially refer to as the W boson, is sort of peaked inside of this core and falls off exponentially fast. It's actually kind of neat. Monopoles are kind of neat because they're sort of one of the few things in the universe that at least I know about whose physical size is significantly larger, is like parametrically larger than their Compton wavelength. Anyways, and I think this actually has to do with the fact that the W boson, essentially it's the W boson is sort of living in some cloud around the monopole to resolve the singularity. Anyways, so very good. So what are we doing now? Okay. So this is sort of the picture of a BPS monopole. So in order to understand the infrared dynamics, we want to look at the perturbations around the monopole background. And it turns out there are sort of 2 degrees of freedom that we need to worry about. The first is the photon, which is, I think, was probably obvious. And the second is there's some charged mode in the monopole core. And one way to see that is to note that the form of the monopole potential I just wrote down is not actually invariant under gauge transformations of the infrared U1 gauge group. Essentially, the point is that, oh, sorry, I made a mistake. So it's not T3, this is T plus or minus. So the IR gauge transformations are generated by T3, which is the diagonal in the SU2, and that does not commute with the W boson component of the gauge field. That's maybe obvious. The W boson has some charge, and so if you do a gauge transformation, it should rotate. So the way you actually make this potential gauge or this monopole gauge invariant under infrared gauge field is you have to add some charge degree of freedom to dress it so that we're sort of working in a gauge invariant background. And this phi, which I'm going to call charge mode, is what we're going to refer to as the Dion degree of freedom. So I argued to you that there's some sort of gut UV completion, and that requires you to have this charge mode that lives inside the monopole core. But you actually need to you actually are required to have something like this from IR consistency. And the reason is that if you try to construct the direct monopole, what you have to do is you have to cut out some hole in space-time, and then you want to impose boundary conditions. And the boundary conditions you want to impose are that there's some magnetic field coming out, and that, well, if you want a monopole, you want the electric field to be 0. However, you're not allowed to impose both of these conditions simultaneously. And the reason is that the electric field operator and the magnetic field operator are just non-commuting variables in the quantum mechanics. So you just can't impose both boundary conditions at the same time. So the way you do this, so that's one reason. And the second reason is that in order to, for example, impose the magnetic field not equal to 0, you actually are fixing the gauge field. And that's just generically not gauge invariant. And so what we usually do is we introduce some charge Goldstone mode on the boundary. And then what you can try to do is to get a monopole by making this charge mode very heavy. There's sort of no obstruction to doing that. And so this is sort of the easiest way to make a monopole. But what it means is that if you excite this this charge Goldstone mode, you actually have a dion. And so when you construct the monopole, you're actually sort of forced to consider all possible dions at the same time. Good. So, so we can see how the UV gut theory does that. It's actually quite nice. So if you actually just take this modified gauge potential with the this dionic degree of freedom plugged in, and you just sort of try to compute what the quantum mechanics is for this Dion degree of freedom. So you just plug this into the UV gut action and just from the kinetic term for the gauge field, and then you integrate over all space-time, you find a quantum mechanics for this Dion degree of freedom. And what you get is a massive, you find that it's a massive field. So here I'm treating phi to have some 2 pi periodicity. And here A is the restriction of the infrared gauge field to the monopole world volume, to R equals 0. Okay, sorry, the writing's taking a while. So what we should think of this is as some massive charge particle on a ring. That's what this quantum mechanics is. And as we know, this is actually an incredibly easy system to quantize. If you look at the Hamiltonian, you get just the free particle Hamiltonian on a ring, and then there's this coupling to the bulk gauge field of the momentum operator. So the Hilbert space is indexed by the momentum modes, which are indexed by an integer. And the energy levels are just when there's no bulk electric field or magnetic field, I guess even, are just given by the sort of standard formula n²/2 times the mass. I apologize for my iPad. But what's interesting about this this system, or well, what will become important about the system, is that we can explicitly see that from the coupling of the gauge field to the momentum operator in the Hamiltonian, that the state n sources a bulk electric charge, which is 2 times n. And this 2 comes from this 2 that multiplies this coupling, and it's a sort of a convention choice where I'm working in integer charge convention where the W boson has charge 2. So this ionic degree of freedom, if you sort of kick it, it's just kicking the mode of the W boson, and so that sources bulk electric charge, which is a multiple of 2. And so this is important because the Callan Rubakov effect is really nothing but the interaction of this ionic degree of freedom with the bulk fermions. Okay. Very good. So now I want to consider coupling to fermions. So since we're working in a spherically symmetric background, what we can do is we can actually do a mode expansion of the fermions in the monopole background. And as I guess the point is that since the monopole background is spherically symmetric, the fermions will decompose into angular momentum representations, and that's very nice because what we can do is we can actually just restrict to the j equals 0 sector. And this is a nice consistent truncation just because the j equals 0 scatters into the j equals 0, and the ionic degree of freedom is also 0 angular momentum, so it should also sort of decay into the j equals 0 sector. All right. So, okay. So the I mode expansion for the j equals 0 sector is incredibly simple, and that's really why everyone has studied it. So let's call our UV fermion psi A. And when we decompose the SU2 doublet into U1 representations, we get some charge fermion. We get charge fermions of plus and minus 1. And our SU2 NF global symmetry breaks into an SU2 NF squared, which acts separately on the positive and negative charge fermions. And the mode expansion explicitly for the for the j equals 0 sector is just given by this simple form. So the positive fermions are incoming only, and the negative charged fermions are only outgoing. Plus there, T minus R. And so here, what I've done is I've sort of, this psi 0 plus and minus, the minus will show up in a second, are the 4-dimensional spinner. It's a constant spinner. the point is that this is polarized along the R direction. Yeah, so one way you can think about this is sort of at a fixed R, you can think of the monopole as sourcing sort of, you have some sort of effective two-dimensional surface and there's a magnetic field coming through it. And what's happening is this magnetic field essentially polarizes the fermions. And what we're doing is we're sort of keeping the lowest Landau level in that system. And so what happens is that the positively charged fermions keep the spin up, and the negatively charged fermions keep the spin down, just because of this level splitting from the magnetic field. And so now once we reintroduce the radial direction, what we find is that there's actually propagating waves that are incoming or outgoing associated to the charge as well. So I've written it in a very suggestive way where this chi and chi tilde are effectively two-dimensional fermions that propagate only in the radial direction. So you can think of a chi mode as sort of a spherically symmetric shell of fermions coming in and out. And so now our four-dimensional scattering problem is effectively a two-dimensional scattering problem. And so we have these chi A's that are incoming and these chi tildes that are outgoing. And it's important that they have opposite charge. And so if you were just to hand this system to a student and just told them there's this two-dimensional theory that has this property, you would well, if it's a good student, they should quickly realize or immediately realize that there's some problem with this. So this is a totally non-unitary system without a boundary condition. And so there's sort of two possible boundary conditions. You could write something like chi is related to chi tilde dagger, where you multiply by some matrix for the for the different, to relate the A index or the SUN 2NF symmetry for the chi fermions to the chi tilde fermions. And the other possible boundary condition is that you're just relating the two using this dionic degree of freedom. And so from the gut perspective, it kind of has to be this one, because this is the one that sort of preserves the, well, this is the one that preserves the symmetries of the UV theory. And indeed, if you just plug in this mode expansion into the action with the monopole connection that I wrote down on the previous page, you can explicitly derive this boundary condition. Okay, very good. However, this sort of leads to a problem, and it's a problem of dynamics. The problem is that what this boundary condition is telling us is that the gauge charge or gauge symmetry is sort of conserved by depositing a gauge charge onto the dion degree of freedom, phi. So the picture is you sort of have some ingoing single chi mode, and then you get a single outgoing chi tilde mode. The difference in electric charge is 2. So you have the dion degree of freedom excited here on the boundary. And but that's a problem because we're working at scattering energies which are way lower than the W boson mass, which is the amount of energy you need in order to actually excite this dionic degree of freedom. So the problem is that phi is parametrically heavy. And so you really can't conserve gauge charge this way. So cannot serve. So in other words, we really have to integrate out phi in order to get the well-defined infrared theory and to understand the infrared scattering. Good. So the way people usually approach this is to use some sort of bosonization. So what we can do is we can write these chi's as some H, capital H field, and we can write the chi tildes as some H tilde field. And then what we want to do is construct some sort of boundary condition that preserves all the symmetries. So if this is JA and this is J tilde A, the boundary conditions we want to write are something like JA times matrix times J tilde B times J tilde equals 0. And indeed, what the Callan Rubakov effect does is literally construct this matrix RAB. And explicitly, it's given by the identity matrix minus the fully populated matrix divided by N times 1 over NF. Okay. Okay, come on. So for example, if we take the NF is equal to 2 case, NF equals 2, so you have 4 fermion doublets in the infrared, or sorry, in the UV, you'd find this matrix R is just 1/2 times this matrix. So it's going to continue writing, but I think you get the picture. It's something that sort of, you have one fermion coming in and it scatters into all possible outgoing modes. So explicitly, we can write this scattering process out in terms of the fields. So in terms of the bosonic fields, it would be H goes to H tilde A minus 1 over the sum over all of the outgoing modes, H tilde A. And so the way you can understand this scattering process is that this first term is the sort of tree level scattering. Chi and chi tilde are sort of related by this mode phi. So the corresponding fermionic condition is chi goes to chi tilde. And then this additional part comes from integrating out the Dion degree of freedom. So this is sort of some sort of phi decay mode, which people have inferred by using the global symmetries of the problem. However, if you sort of look carefully, when you fermionize this, and go back to sort of, the original language that we're working with, this part of the scattering process looks really weird. What it is the product over all of the chi tilde modes, well, the complex conjugate of the chi tilde modes, and then this 1 over NF tells you to take the 1 over NF root of this operator. And so that is very strange. And so there's sort of been multiple ways, as I said earlier at the beginning of the talk, there's sort of multiple ways to try to interpret this. The first, well, essentially, people have been sort of mostly focused on this first case or this first language until recently. So in the bosonic language, it's sort of unclear that there's really any problem, except for the fact that you sort of get these states that look like they have fractional fermion occupation number. And so this is where people have been saying it's something about, vacuum fluctuations, or maybe some sort of soft radiation. But the second, well, back to the fermionic language, makes it much more clear that there's something seriously wrong. And so this is sort of where the idea is that there's some topological line attached to the outgoing modes. Comes from. Essentially, the idea is that if you take some operator in a quantum field theory, it's not necessarily well defined to take its square root or its nth root. You're actually generically not allowed to do that. You can just, for example, take the mode expansion. That just sort of doesn't make sense. That doesn't mean, okay, that doesn't mean it cannot make sense, but it generically doesn't make sense. And so usually the procedure you have to follow if you're going to try to take the nth root of an operator is you actually have to gauge a Zn zero form symmetry. Essentially what this gauging the Zn zero form symmetry does is it reminds you that you're not allowed to take the nth root of an operator. And so my understanding is that this is where the topological line really originates from, because what's happening is that this topological line introduces a branch cut in all of your correlation functions, which is generically what happens when you take the nth root of some analytic function, you get branch cuts. And this topological line is just the operator version telling you about this branch cut. So from the gut perspective, or rather in the setting of a gut theory, where the Callan Rubakov effect maybe came from, this is super confusing because a sort of in 2 dimensions, if we have some sort of topological line, which maybe we can think of as some sort of branch cut in our correlation functions, if we try to go back to 4 dimensions, this becomes a topological surface. So that is a 3-dimensional surface. So you have sort of a branch surface. So you have some sort of space filling singularity in your correlation functions in the sort of full 4D description of the Callan Rubakov effect, if this procedure, in this proposal. Okay. So I'm sorry, I'm running a bit slow. I guess it's not helping that this is running slowly. Okay, so now what I want to do is sort of propose a new way to think about this. So if we go back to the quantum mechanics, or the Dionic degree of freedom, now we had some Lagrangian, which we're very familiar from school. So we have the charged particle on a ring. And the charged particle on the ring actually admits an additional term that we sort of, well, it admits a topological term, which is just a 1-dimensional theta angle. And this has the effect of changing the momentum operator and what it does is it shifts the momentum operator by a constant. And it's also known what the Hamiltonian is when you add this deformation. It shifts in this nice way. And so what we see is that because of this shift in the Hamiltonian, if we start at theta equals 0, the ground state is given by the 0 state. But then if we shift theta by 2 pi and go to theta equals 2 pi, we see that the ground state is actually the 1 state. And we know that the 0 state has 0 electric charge. Oh, I apologize. My iPad's way behind. I'll just let it catch up. In the meantime, are there any questions? Yeah, sorry. Next time I give a talk again, I'll try to fix this. Okay, it's caught up. Very good. Right, so the 0 ground state has electric charge 0, whereas the 1 state has bulk electric charge 1. So that's kind of cool. And one way to understand this in terms of how it appears in the Callan Rubakov effect is that this theta actually comes from a 4D theta angle. So if you just write out the 4-dimensional theta angle interaction, you can decompose it into the electric and magnetic components. And then if you integrate if you reduce along the sphere where you integrate over the magnetic field, then you'll end up with something that's only dependent on the radial electric field, which is a total derivative in the 2-dimensional half space. And when you peel off the derivative, you'll find that this is exactly equal to the theta term that I wrote down, up to a multiple of 2. And so, right, so why am I talking about this? And when you have massless fermions, the theta angle is thought to be sort of meaningless because you can get rid of it with a field redefinition. And that's true. But for massive fermion, that's not the case. This is sort of secretly one of the reasons why I wanted to consider massive fermions. So in 4 dimensions, you can get a theta term from a CP violating mass for fermions. So if you take fermions with some complex mass, and I'll write the mass as having some phase alpha. We know that this that you can just do a field redefinition or a chiral transformation of the fermions to move this complex phase into the 4D theta angle. However, instead of doing this, what you can do is you could just, if you think about, you can put the phase into the theta angle and then integrate out the fermions. Alternatively, you can just straight up integrate out the fermions. And what you find is that there's this phase, or rather the Witten effect, shows up in the fermion vacuum. What you find that there's actually an electric charge density in the fermion vacuum, which is localized around the monopole, which falls off exponentially. And the total charge actually gives you exactly the same amount of electric charge around the monopole as you would have deduced from the actual Witten effect. And so my claim is that what happens is that the Callan Rubakov effect, or the scattering of fermions, actually induces a sort of theta term dynamically. And this is how the gauge charge is conserved in the monopole fermion scattering. Okay, so I'm running a little bit low on time. So I'm just going to skip some of the details of how you actually can derive this. And so we can just write down the action actually from all of the components we already had. So if we work in the bosonized frame, so we can write HA, little HA is the sum of H and H tilde, which is an uncharged field. And I'm also going to write lower h without any index as sort of the total bosonic field. So the action for the two-dimensional action for this scattering process is just given like this. So I'm adding here now a mass term. And I'm also adding the gauge interaction. So everything sort of couples together to the gauge field. And then there's this kinetic term for the gauge field. And now we have the quantum mechanics part. And instead of having a theta angle, what you have is you have some boundary interaction, where this is the value of H, this total bosonic, okay, sorry, I'm getting ahead of myself again. Good, so here's the interaction that I was talking about. So what you find is that the boundary value of H actually plays the role of this dynamical theta term in the monopole fermion scattering. And so what's happening is that in the bosonic language, a chi mode is an H kink. So here, I mean, you have some soliton like this that is scattering inwards. And similarly, a chi, I said psi, I meant chi. I guess they're the same thing. And similarly, a chi mode is an H tilde kink, which is outgoing. Oh, sorry, it's upside down. So what you find is that if you do the scattering, chi goes to chi tilde, that corresponds to an H kink reflecting off the wall into an H tilde kink. And what that does is it corresponds to a winding shift of H, which is given by 4 pi. And so in particular on the boundary, this looks like a shift of the one-dimensional theta angle, which is 2 pi. And what that means is that if you started in the monopole vacuum 0, what you end up with is a monopole whose vacuum state is given by the 1 state. And so we find that the electric charge, the difference of the electric charge of scattering chi into chi tilde is actually made up by this shift in the vacuum state of the monopole. And so this seems a bit weird, but we actually have total control. Since we worked in the full mode expansion, we have total control over all the fields. So if you literally just trace back where the H comes from in terms of the 4-dimensional fields, so chi is e to the IH, and similarly for chi tilde. But chi is just the sort of mode. It's literally just the mode of psi, right? We said psi has this 1 over r profile just because we're in spherical coordinates, times chi times some constant. I guess we don't plus here, times some constant spinner. So we find that this is, if we just put H in here, it's literally the phase mode of our 4-dimensional spinner. So the physical picture here is that when you scatter in psi, its phase mode is just rotating. And so when it bounces off the monopole, it turns into the psi minus, whose phase rotates the opposite direction. And so what this does is it leads to an effective 4D theta angle, which shifts by 4 pi. You can think about this as really just an axionic mode. And when you scatter an axion, it's going to change the electric charge of the monopole. And so my proposal for the resolution to the Callan Rubakov problem is really that if you have some psi plus mode that scatters off the monopole, whose vacuum state for psi is theta equals at theta equals 0 equals 0, what you find is that you get some psi minus mode coming out plus m, where now the theta has shifted by 2 pi in the one-dimensional quantum mechanics, so that the vacuum mode, or the vacuum state of the monopole is the one state. And what you should think of is that this is like psi minus coming out plus a dion of charge 2. And so this is critically important to have a mass, because this sort of charge cloud sort of gets cut off by the mass of the fermion. And so it's sort of only, I mean, the scattering process only really makes sense as being over after they're sort of separated larger than their Compton wavelength anyways. So what you see is that there should be this electric charge that's sort of deposited on the dion. And so, or sorry, on the monopole. And good. So essentially my proposal is that what happens is the fermion, when it comes in, it scatters off the monopole and it has this tree level interaction with the W boson. And that's sort of how this tree level part happens. And then there's this sort of shift of the fermion vacuum due to this phase rotation. And that sort of allows this spectral flow in the quantum mechanics on the monopole that allows you to conserve the electric charge. And over my time, so I guess I want to make a couple final comments. The first is that if you take this limit where the fermion mass goes to 0, sort of everything starts to make much less sense. You find that the charge radius of the electric cloud around the monopole goes to infinity while remaining a constant total charge. So this is potentially one of the reasons why this was sort of it's sort of been a very confusing problem for so long, is that maybe you need an IR regulator to make sense of it. Another comment I want to make is that the proposal actually preserves all symmetries, and the asymptotic states sort of obey this nice, well, they behave exactly like you'd expect. They're sort of given by the free field quantization that you'd like. And also, since it preserves all symmetries, it actually matches Callan and Rubakov's proposal sort of when their proposals made sense. So if you look at the Callan Rubakov proposal and you just keep scattering fermions, at some point you would find that there's some integer number of fermions coming out, and then you'd see there's no issue. My proposal matches that exactly, because when the dion, essentially the idea is that when the dion accrues enough charge, it can actually decay into the bulk fermions. And the reason why it doesn't decay when there isn't enough electric charge on it is because all of the fields in the infrared couple to bundles of the form of this form. So what you find is that there's this sort of Z2NF redundancy, or in other words, the gauge group gauges a Z2NF subgroup of the SU2NF flavor symmetry. And so what that means is that any interaction that carries away gauge charge is necessarily going to break this SU2NF flavor symmetry. Or conversely, any gauge invariant interaction must preserve at least the part of the any SU2NF preserving interaction will also sort of preserve the gauge interaction, and this sort of prevents you from carrying away electric charge without breaking a bunch of symmetries. Is there anything else I wanted to say? Yeah, so my final few comments are that in my paper I actually generalize or argue that this analysis generalizes to the higher angular momentum modes. And what else did I want to say? Sorry. Oh yeah, and then also I wanted to say that if you look at some scattering energy, which is close to the mass of the fermions, what you find is that actually, so the energy that's deposited in the electric field is also of order of the fermion mass. That's just because you have a charge cloud of unit charge that's of size 1 over the fermion mass. But what that means is that essentially the fermions can get trapped by this ionic potential. So if you, my proposal sort of suggests that if you scatter in a fermion at low enough energies, it'll actually just get stuck on the monopole, which is kind of neat. But this definitely requires more investigation. And then, so my very final comment is that it would be very interesting to study the sort of case when there are Yukawa interactions, because that would lead to a very phenomenologically different scattering problem, such as just because there are truly fermion bound states. And it would also allow us to sort of study this effect using supersymmetric theories. And in particular, you might be able to study this effect in quiver gauge theories. And so, that's, I think I'll stop there. So thank you very much.
All right, let's thank Daniel. Do we have questions? So for this bound state you mentioned at the end, is the idea that if you then throw in like a very highly energetic fermion, that you can bounce the other one out? Or
yeah, I think you should be able to. Yeah, so I sort of only considered the case where you scatter a single fermion, just because once there's an electric charge, the mode expansion totally changes. But I mean, once you're at higher enough energies, it really shouldn't matter anyways. You just you have maybe some electric barrier, but you throw something in and it just should bounce off. And yeah, so yes, I think so.
Okay, cool. Nice.
I think that someone told me that there's a group at Maryland who's doing a computer simulation of this. So I think we should soon, well, soon is I guess relative, but we should soon find out if this proposal is right or not.
I see. Okay, very nice. It's almost an experiment.
Yeah, exactly. Yeah, Ethan.
Hi, thanks for the nice talk. So this is just kind of a vague question, but what's would you say is your issue with the Zohar Marike proposal of this topological line being attached?
Right.
I mean, I assume it's because you want no change in the outgoing Hilbert space, but what exactly goes wrong?
Right. So I don't have any problem with their proposal. Well, I think especially their work I think is very fascinating in the two-dimensional context. Right. And so we also took very different perspectives. They were sort of working from an IR perspective going up and trying to think about anything that could possibly happen. Or I was saying, I'm going to just fix my UV physics and say, like, what actually happens in this theory? So those are sort of very different takes from that perspective. So as I was saying during the talk, the reason they add this topological line is because when you sort of just take Callan's answer, I guess it was actually Callan who did this, you find that this outgoing operator is some operator that's not allowed in your theory. And so I guess sociologically, the way you would fix, if you just assume that this is the correct analysis, you would have to add this topological line to it. And so in this sort of four-dimensional perspective, it's very confusing to me how you would add a topological surface, or what the physics is that would add this topological surface, because it sort of introduces a space-like filling singularity in correlation functions. And that sounds bad from a semi-classical four-dimensional perspective. It doesn't mean it's not there. It just means you'd have to have some very, very weird UV physics inside the monopole.
Okay, I see. Thanks. I haven't deeply analyzed either paper. It's just yeah, to get a kind of sense of. Yeah. Okay, thanks.
Yeah, sure, no problem.
Any more questions? All right. I would say in that case, let's thank Daniel again.
Thanks.
Who, despite iPad troubles, managed.
Yeah.
Okay.
Modern
Off the
technology.
record.